All right, so let's get started. So we're going to continue with interior point methods today. The only administrivia is that the midterm solutions are posted. I don't remember whether we announced that before, but I wanted to remind everybody. All right, so let's review where we were at the end of last class. So we were talking about the Analytic center, which is the minimum of the log barrier function for a set of inequalities. You can think of it as there's a force from each one of the inequalities pushing the analytic center away from it, and the analytic center is where all of the forces are in equilibrium. And we can find the analytic center using Newton's method quite quickly. The Newton iteration is right here. So it's basically, you have the constraint matrix A, you reweight it based on the current value of your variables, and you take a step. We also talked about Deichen ellipsoids. So the Deichen ellipsoid at any point is contained within the feasible region. It's defined to be the unit ball of the Hessian norm for the log barrier at that point. So it's a useful way to get sort of a local idea of what the shape of the feasible region is. And in particular, the Deichen ellipsoid at the analytic center is nice because it's guaranteed to contain a fraction of the volume of the feasible region. In particular, if you scale it up by a factor of m, then it will contain the feasible region. And of course, like any other Deichen ellipsoid, it's contained within the feasible region, so it makes a nice inner and outer bound on the feasible region. Okay? So that's the Deichen ellipsoid. We also talked about the central path. And the central path is just like the analytic center, except you add a multiple of the linear objective. So instead of finding the center, you find the center sort of pushed in a little bit in the direction of the objective. And the amount by which you push it is the parameter t, which trades centering versus optimality. So at one extreme of t, you get the analytic center. At the other extreme of t, you get the LP optimum. And in between, there's a nice smooth path. Right? And so our idea today is going to be to follow that path so that we can pick it up somewhere near the analytic center, which is relatively easy to find, and follow it along until we get to the LP optimum, which is harder to find. Okay? Everything that I've talked about so far, the analytic center, the central path, and the Deichen ellipsoids, these are all affine invariant, meaning you can take any linear transformation and any offset of the feasible region, and it doesn't change them, or rather it changes them by the same linear transform. We talked about the constraint form versus the penalty form of the central path. So the penalty form is you add t times the LP objective. And the constraint form is you say the LP objective is better than some cutoff lambda. And either way, you get the same central path. One form is sometimes more convenient than the other. And finally, we ended with the Primal-dual correspondence for the central path. So if you take the dual of the central path problem, you get another central path problem for the dual linear program. And there's a nice correspondence between points on the two central paths. So in particular, for the same value of the parameter t, you get analogous points on the central path in the primal and the dual, and you know that the gap, so they're both feasible because they're on the central path, which is contained in the feasible region, and their duality gap is m over t with m constraints. And so if you find a point on the central path in either the primal or the dual, you can immediately find the corresponding point on the other central path, and you can get a bound on how far away either one of them is from optimal. Okay? All right, so that's the review. Any questions, lingering questions from last time? All right, so let's get to new material. So we talked about the primal-dual form of the central path, and I wanted to go into a little bit more detail because it's going to be useful both for understanding and for designing algorithms. So we have here a primal-dual pair of linear programs, minimize C transpose X such that AX plus B is bigger than or equal to 0, component-wise, or maximize minus B transpose Y subject to equality constraints on Y, and Y has to be non-negative. Okay? And the KKT conditions for this primal-dual pair, it has to be X has to be primal feasible, Y has to be dual feasible, and then to get optimality, we have to have strong duality, right? So the objective value in the primal is equal to the objective value in the dual, right? So C transpose X equals negative B transpose Y. And in fact, we can relax that to less than or equal to 0 here because we're never going to be able to get better than 0. We're never going to be able to get a primal point which is better than a dual feasible point. Okay? I don't remember whether we talked about relaxing these, but one obvious thing that you can do is to relax these conditions to say that the duality gap has to be less than or equal to lambda, right? If lambda is 0, then you get an optimal pair. If lambda is 10 to the minus 5, then you get a pretty good pair. If lambda is 10, you get a mediocre pair, right? And so one thing I wanted to point out here is that everything I've written here is a linear equality or inequality, right? So the KKT conditions, we can think of them as just another linear feasibility problem, which is kind of interesting, right? Because we said a long time ago, a number of classes ago, that linear feasibility is just as hard as linear programming, right? The optimization doesn't add any power. And here's another proof of it, right? We took a primal-dual pair of optimization problems, and we turned them into a feasibility problem. Okay? And this is actually, I like this reduction better than the one we used last time around. So last time around we used binary search on the value of the objective. So this is reducing to a single linear feasibility problem, right? For complexity theorists, it's a CARP reduction rather than an oracle where you're calling the calling linear feasibility repeatedly, right? So we just do one tail call to linear feasibility at the end, and we can still solve a linear programming problem. Okay? Was there a question here? No. Okay. So we can find the optimal point by looking for the analytic center of the KKT conditions, right? We can just pass this to our analytic center finder. The problem is that there's no strictly feasible point for the KKT conditions, right? We know that we can't satisfy this constraint strictly, right? We know that we can't have a primal feasible point that's better than a dual feasible point. So that's why it's nice to have this relaxed strong duality, because if the original problem had a strictly feasible point, now this relaxed KKT conditions will also have a strictly feasible point. Yeah?
Why did we bother expressing it as an inequality if we allow equalities anyway?
So that, if we expressed it as an equality, then this constraint would be okay, but then there wouldn't be any strictly feasible point for these inequalities. We'd just be pushing the problem somewhere else. So because this equality would then push X right hard up against one of the inequality constraints.
But the other way around, is there a reason for that as an inequality?
So that we can relax it here. Because if we said equals lambda, then we would say, I don't want to find anything that's better than lambda, right? I want to find something with exactly this gap. We could do that. That would work fine. But this is sort of more convenient because it lets us take something good if we happen to find it. Okay. So it's a good question, though. This would all probably work if you had equality here, but I wrote it this way because I wanted to make the constraint as weak as possible. Okay, so now we have a strictly feasible set of linear inequalities and equalities. So we can run our Newton method to find the analytic center. And if lambda is small enough, we've got a solution to our linear program. And of course, the problem, you can't get something for nothing, is that as lambda gets smaller, the conditioning gets worse and worse. There gets to be only a smaller and smaller feasible region, and so the Newton method for the analytic centering problem gets slower and slower. So what we're going to do for the rest of the class is derive an algorithm where we can essentially adjust lambda as we want. Now, so here's this relaxed KKT condition. So let's look at the analytic centering problem in a little bit more detail, right? So this leads to a penalty, right? We want to minimize the sum of log si here, right? And here we want to minimize the sum of log yi, right? And then here, this will lead to minus the log of lambda minus C transpose X minus B transpose Y, right? Now, the interesting thing is, here, the primal variables appear here, right? The dual variables appear here. And the only mixed thing is this constraint here, right? So what I'm going to do is I'm going to use dual relaxation to get rid of this constraint, right? Lagrangian relaxation. And that will separate the primal and dual back, and it'll give us another little bit of intuition. So in particular, I'm going to skip this because you've seen derivations like it a ton of times, but you can prove that minus the log of z is greater than or equal to minus tz plus 1 plus log t, right? So this is basically saying that minus log and plus log are conjugates of one another, but I've rearranged it a bit to be in a more convenient form. Okay, so this here, I can bound it by minus t times this thing, so I'll just turn it into t times the negative of this thing. So C transpose X plus B transpose Y minus lambda, right? And then plus 1 plus log t, right? And so now, what's happened? I have t times C transpose X, right? So I can take this term and put it in with the primal variables. I have t times B transpose Y, so I can take this term and put it in with the dual variables, right? And now I have two separate problems. And you should recognize these problems, right? So TC transpose X minus the sum of the log slacks, that's exactly the central path problem for the primal, right? And TB transpose Y minus the sum of the log dual variables, that's exactly the central path problem for the dual, right? And so what I've shown here is exactly that if we find the analytic center of the relaxed KKT conditions, that's exactly the same as finding corresponding points for some value of T on the primal and dual central paths. Okay? So this is, you can think of this as being the constraint form, and this as being the penalty form of this KKT problem. And with the penalty form, it splits into separate primal and dual pieces, right? And so this shows you that the analytic centers of this problem are, in fact, exactly the analytic centers of the primal and dual analytic centering problem. Sorry, exactly the points on the central paths of the primal and dual. And just as before, it turns out that there's a mapping between lambda and t. But this time, we can actually compute the mapping. I'm not going to do it, but basically, we have that lambda is equal to m plus 1 over t if there are m constraints, which means that it's equal to m plus 1 over whoops. Let's forget that. So lambda is m plus 1 over t, right? And so we can compute the duality gap from either t or lambda, and we can go back and forth between the t and the lambda forms. Okay? So that's kind of cool and somewhat surprising.
So did you prove this, or are you not?
I'm going to skip that. Well, let's take a look. I can prove it. No, no, I did not prove it. The proof is relatively simple, right? We know that just from the gradient of this, right? We know that, take the gradient with respect to t, we know that we know that C transpose X plus B transpose Y minus lambda, that's not a lambda, lambda plus 1 over T is equal to 0 at the optimum, right? And so, and then we know that at the particular primal and dual ones, we know that the duality gap is m over t. We proved that last time around. So we know that m over t plus 1 over t is equal to lambda, right? And that's exactly what I wrote up here. Okay, so we can prove the relationship between the primal between lambda and t, and we can find any point on the central path, either primal or dual, using the analytic center of one of these relaxed KKT conditions. All right. So based on what I've said so far, we can now write down a pretty simple algorithm that actually turns out to work pretty well. So the algorithm is we're going to set t equal 1, or some arbitrary number, set y to be a vector of all 1s, x to be a vector of all 0s. So this is not a feasible starting point for the dual central path problem, or not typically. But we can use an infeasible start Newton method now to find some point y on the dual central path that corresponds to this value of t. Right? And we'll also get, as a byproduct of Newton's method, the corresponding value of the Lagrange multipliers x. Right? And we know that once we've done that, these multipliers are going to be primal feasible. So we found both the primal and the dual central path point. And there'll be a duality gap of m over t. Right? We proved that last lecture. And so that's good. If m over t is small enough, then that's fine. We can stop. Otherwise, we can multiply t by some constant, right? And hope that now, so that changes the point on the central path that we're looking for. But we hope that we're still in the region where Newton is converging quickly, right? We hope we're sort of, because of this warm start, we hope that we're able to only use a few more iterations of Newton to find this new point on the central path and keep going. Just keep multiplying t by some constant, finding the corresponding point on the central path using warm start from the Newton's method, and stop when t is so big that we're happy with the duality gap. Right? So does the algorithm make sense? Yes? Okay. So this algorithm is in the textbook, the Boyd and Vandenberg, and there's a proof of this algorithm in said textbook. The proof spans, I think, 2 different chapters, so I'm not planning on covering it today. And there's some nice intuition, actually, in the proof. The biggest one is that there's this property called self-concordance, which is basically so an example of a self-concordant function is minus log. And what it means is that basically, invariant to whatever the scaling is, there's a way to bound the derivatives of the function, basically to bound the third derivative in terms of the second derivative. And what that lets you do is put bounds on how bad the Newton approximation is, right? So if you approximate it using a second-order Taylor series, what matters is how big the third derivative is, right? Because that tells you how quickly you get out of the range where the quadratic is a bad approximation. And using that bound, you can say, well, if we use Newton's method and take, steps that are of bounded length, then they're going to actually decrease the function at a relatively rapid pace. So that intuition is concisely wrapped up in 2 whole chapters of Boyd and Vandenberg. So instead, what I'm going to do is do a different algorithm and a different proof today, which I think are actually much more intuitive and helpful. And you can let me know after lecture whether I'm right. Okay, but before we do that, this is a figure I copied from Boyd and Vandenberg. They just ran this algorithm for problems with 50, 500, or 1,000 constraints, right? And so you can see it takes 10 or 15 Newton iterations, and then they drop the gap, right? And so here they started with a duality gap that was 10 to the 3 or so. After 10 or 15 iterations, they found a point that was around 10 to the 1, right? And then after another 10 or 15 iterations, they found a point that was around 10 to the minus 1, right? And so very rapidly, we're reducing the duality gap. It doesn't seem to make too much difference how many constraints there are, right? The time it takes for each Newton iteration depends on how many constraints there are. But the actual number of Newton iterations that you need, very little dependence, right? So this is it's a nice algorithm. You can see lots more pretty plots in Boyd and Vandenberg. But instead, we're going to analyze this one. So for the KKT conditions, we can divide them into two parts. One is feasibility, right? So this is primal feasible and dual feasible. And then the last one is optimality, right? And these two are equivalent, right? So this is the actual duality gap, but you can actually transform that into S transpose Y, right? Because so we have S is equal to AX plus B, right? So S transpose Y then is equal to AX plus B transpose Y, right? And then Y transpose A is C. Sorry, A transpose Y is C, right? Y transpose A is C transpose. So then this is equal to, this term becomes C transpose X plus B transpose Y, right? So these two forms, these are equivalent. And so what we're going to do is we're going to do what's called a potential reduction algorithm. We're going to make a potential function which measures both how feasible and how optimal a point is. And we're going to start at some value of the potential and have our algorithm try and reduce the potential over time so that at the end we're guaranteed to have a point which is both very feasible and very optimal, right? Yes, right. I know you can't have very feasible and very optimal. So, right, this term here, if Y transpose S is small, right, that means that you're close to optimal, small duality gap. Log is a monotone transformation, so it doesn't change that. It means we want to push this term to negative infinity, right? And here, right, these are the barrier terms that keep you away from these inequality constraints and maintain feasibility, right? And K here is a parameter that tells you how much you weight this optimality term versus these feasibility terms. All right. So just to show you what this potential reduction is going to do, right? So I can take this potential and I can split the m plus k log Y transpose S into two terms, right? And group them like this. And I'm going to call this part. Oh, actually, So let's take a look at this term in the brackets, right? So this term in the brackets, you can basically prove that it is greater than or equal to 0. You can use convexity. You can use the arithmetic geometric mean inequality, right? Because if we take e to this, we're going to have a sum and a product here, right? But you can basically show that this term is bigger than or equal to 0. I'm going to skip that because it's not that enlightening, which means that the whole potential is bigger than or equal to k log Y transpose S, right? And so if we make the potential very small and have a feasible point, right, that means that log Y transpose S is going to be very small, and we're going to be close to optimal. So in particular, we're going to start with a strictly feasible point, right? We're going to assume somehow that we know how to prepare one. I'm not going to talk about how to do that, but there are ways to do that. We're going to update it repeatedly, so we're going to compute a Newton-like update and show that each one of these Newton updates is going to reduce the potential by at least some amount delta, right? And so that means that at any time we have that P is less than or equal to P0 minus the number of iterations times delta after t iterations, right? And here, right, that means that k log y transpose s is less than or equal to p0 minus t delta, right? And so that means that y transpose s is less than or equal to the exponential of p0 minus t delta over k, right? And so the complementarity, the distance from optimality, is going to go down exponentially fast with iterations, right? We need logarithmically many iterations in 1 over epsilon to achieve any desired accuracy epsilon. Okay? So at each one of our updates, we're going to take care to maintain strict feasibility, right? So that means that A transpose delta y is equal to 0, and delta s is equal to A delta x plus b, right? So we started feasible, we maintain feasibility, and we keep improving the potential, which gives us a bound on how far from optimal we are. So the basic strategy of the algorithm makes sense? Cool. Oh, I should point out, by the way, that this is based on a paper by Kojima, Mizuno, and Yoshise in 1991. So if you want tons more information about this algorithm, you can go there. But hopefully you won't need it after I'm done with the lecture. All right. What? I'm sorry? Capital T? This is the number of iterations. Right? So if we go down by delta every iteration, then we will have gone down by t delta after t iterations. Okay. Okay, so how are we going to make sure that we reduce our potential on every iteration? We're going to make an upper bound on our potential, and the upper bound will be a quadratic. And it won't be valid globally, but it'll at least be a locally valid upper bound on our potential. The quadratic is going to be very, very familiar. It's going to look a lot like the Newton's methods that you've seen in the previous couple of classes. And we will just be able to analyze this upper bound to show, right, if you just look at the quadratic, solve it, and show that the decrease is at least a certain amount. Okay? So we're going to split the potential into two terms. I'll call this part P1 and this part P2, right? And we'll upper bound each one of them separately. I should point out, by the way, that P2 is convex, right? But P1 is not, because it has a cross product between y and s in it. Okay? So, but we're still going to, we'll manage to upper bound it anyway, even though it's not convex. So in particular, so actually we'll do this one first, right? So we know that just because of the Taylor bound on log, we know that the log of, for any z, the log of z plus delta z is less than or equal to the log of z plus delta z over z, right? The gradient is 1 over z, so you multiply the change by the gradient. This is the value at z, so this is the this is the Taylor upper bound to the log function at a point z. Okay? And so we'll just use that. It's less than or equal to m plus k times, so z is now y transpose x, so this will be log y transpose s, log y transpose s, right, plus, so delta z, right, that's going to be the new value of y transpose s, so y plus delta y transpose s plus delta s, minus the old value, y transpose s, and then all of this is going to be divided by the gradient, which is y transpose 1 over, multiplied by the gradient, which is 1 over y transpose s, right? Does that make sense? Now, this term here, right, I'll just expand it out a little bit. We have 1 over y transpose s, right? So that's this term that I'm going to be looking at. And then so we have inside a y transpose s and a minus y transpose s. Those cancel each other. So we have now delta y transpose s plus delta s transpose y, right? And now we have delta y transpose delta s, right? And, whoops, delta y. Okay. And I should point out that if we look on the previous page, right, we had that delta y is in the null space of A, right, null space of A transpose. Delta s is in the range of A. And so that we know that delta y and delta s are orthogonal to each other because the range of a matrix and its null space are orthogonal, right? And so here, this delta y transpose delta s just goes away. Okay? So we now have, for any fixed value of y and s, we have an upper bound that's linear in delta y and delta s of this term. Yeah? Right, s plus delta s and y plus delta y. Thank you. Okay, so now we have the other term, right? This is minus log yi minus log si summed over all dual variables and slacks. Okay, and here we're going to use a very familiar strategy. We're going to use Taylor expansion, second order Taylor expansion, just like in Newton's method, right? So if we take the gradient, right? So dp2 by dy, right? That's equal to minus 1 over y. That's taken component-wise, right? So just the reciprocal of every element of the vector y. dp2 ds is equal to minus 1 over s, right? And then the Hessians are d squared p2 dy is equal to, and now I'll write capital Y for the matrix with y along its diagonal, and so it'll be y to the minus 2, right? We'll take 1 over each element squared, we'll string them out along the diagonal of a matrix, and that's going to be the Hessian, right? And then the same thing, d squared p2 by ds is equal to s to the minus 2, where again capital S is the matrix with little s strung out along its diagonal. And then there's no cross term, right, in the Hessian. The second derivative dy ds is 0. Okay? So we have now that P2 is approximately equal to minus the sum. So let's actually be explicit about this, right? So this will be s plus delta s and y plus delta y, right? And so it's going to be approximately equal to minus the sum of log yi minus the sum of log si. That's the constant term from the Taylor expansion. Plus the first order term, right, which is going to be minus delta y transpose 1 over y, right, minus delta s transpose 1 over s, right? And then the quadratic term is going to be based on this Hessian here, right? So it's going to be plus a half delta y transpose y to the minus 2 delta y plus a half delta s transpose s to the minus 2 delta s, right? So this is a nice Taylor expansion, and it's only an approximation, right? It's neither a lower nor an upper bound, but it turns out that if we just multiply the Hessian by a constant tau, right? So there's some parameter now, tau, which is greater than or equal to 1, right? Actually, let's make it strictly greater than 1, Okay, so we can turn this approximately equal to into a less than or equal to. And here's a picture here. I chose tau equal 2, made the approximation to log at 1, right? And you can see it's actually quite close over here. It's going to curve up here and be nowhere near as good an approximation over here. And it's valid then over some range that's going to depend on tau, right? The bigger we pick tau, the wider a range it's going to be valid for. Okay? And in fact, I'm just going to take tau equal 2 for simplicity. And then this will be valid whenever delta y over y is greater than or equal to minus 2/3. And the same thing for delta s over s. Right? So in other words, here, if you plot 1/3, it's somewhere here, right? And so the crossover point doesn't come until the left of 1/3. Okay? So we now have a quadratic upper bound on the P2, and we had a linear upper bound on P1, right? So together, we've got a quadratic upper bound on the whole potential that's valid in some region around our current point. Okay? And so I will call this thing here, I'll call this P2 bar, right? And here, this I'm going to call P1 bar. And so now our algorithm is going to be to keep repeating until we're tired, choose our increment to minimize P1 bar plus P2 bar, subject to maintaining feasibility, and then we're going to make a constraint. This is an ellipsoid constraint on delta y and delta s. And 2/3 was the distance that the approximation on the log was valid for. And this ellipsoid is going to be, so on here, right, this was just component-wise, it had to be bigger than or equal to minus 2/3. So if we put it in an ellipse of radius 2/3, that's going to be a much stronger constraint, right? So this is stronger than that box constraint that we had before. So if we do this, right, then we're going to guarantee that we decrease the actual potential by at least as much as we decrease this bound on the potential, right? And then we have this direction now. We'll step along it while maintaining feasibility. And the claim is that we can also always decrease this potential by an amount delta equals 1/4 per iteration. Okay, I haven't proven that yet, but I will prove it soon. And so it makes sense that if I can prove that, then I will have proven that this algorithm works, right? All right. So why might we be inclined to believe that this potential can be decreased by at least 1/4 on each iteration, right? So for intuition, let's look at a really simple case. A case that we can get some nice geometric intuition for. So let's suppose that our slacks are the vector of all ones, our dual variables are the vector of all ones, right? And then just copying from previous slides, P1 bar is P1 plus, and now 1 over y is the vector of all ones, 1 over s is the vector of all ones, and we had m plus k we had m plus k was the constant. And I think, right, this is just y transpose 1 over y, so I think I put an extra factor of m here, which is going to appear later, so that's a cut and paste error. Sorry about that. And then P2, again, this is, if we look on the previous slide, right, oh, sorry, there's a 1 over y transpose s, right? So with y equals the vector of all ones, s equals the vector of all ones, y transpose s is m, and so that's where that m came from. So let's, so I don't have an eraser on this thing, so just ignore that. And for P2, right, we had Right, so this was y transpose 1 over y, s transpose 1 over s, delta y transpose delta y, and delta s transpose delta s, right? And so I have tau equal to 2. This was tau over 2 times these terms, and I just canceled it. Okay? And so if we just add these together, right, we get that the whole thing is we have an m plus k over m here, right? And we have an m over m here, right, as a coefficient of 1 transpose delta y. So we have k over m 1 transpose delta y plus k over m 1 transpose delta s, right, plus the quadratic part, delta y transpose delta y plus delta s transpose delta s, right? So this is nice and simple, right? We have a spherical quadratic here, right? And we have the all ones vector, a multiple of the all ones vector as our gradient. So how much decrease is going to be possible? Well, if there were no constraints on delta y and delta s, we'd just step the appropriate distance along this gradient to reach the minimum of the quadratic, right? So what's gonna make the difference here is how big is the projection of this linear term, the gradient of this linear term, how big is its projection onto the feasible set, right? So the feasible set was A transpose delta y equals 0, and delta s is equal to A delta x. So let's draw it, right? So here is the point 1, 1, which is both y and s, right? And here's the gradient vector. It's a multiple of the all ones vector, right? And delta y, right, is somewhere in this subspace because it's in the null space of A transpose y. Delta s is somewhere in this subspace, right? And so the optimal values are going to be just to decompose this thing into its orthogonal components along each one of these two subspaces, right? And so this is going to be some vector alpha. This is going to be some vector beta, right? And we know that the length of alpha squared plus the length of beta squared is equal to the norm of our gradient vector squared, right? And so in particular, we're going to be able to so what is the length of this projection of the gradient onto these two subspaces? Well, it's just the projection is just going to be the vector alpha stacked on top of beta, right? The gradient with respect to delta s projection is going to be alpha, and the projection onto the constraint for the delta y is going to be beta. And the norm of that is exactly the square root of alpha squared plus beta squared, right? So it's exactly the same as the norm of G. Okay? And we know what G is. It's the all one vector multiplied by k over m, right? So the all one vector has a norm of the square root of m times k over m. And so this is going to be k over the square root of m. Okay? So just going back, what I showed was that for this particular special case, the projection of this linear term here onto our constraints has a norm which is lower bounded, right? As a matter of fact, we calculated it exactly. The norm is k over the square root of m. And so that's going to tell us how much we can decrease this quadratic, right? The bigger the gradient is, the more we can decrease the quadratic. Okay? So does that intuition make sense? Yes? No? People look somewhat stunned. Should I try explaining it again? So the problem here, right? So we've got our quadratic approximation, right? So our quadratic approximation to our potential is doing something, right? Whatever it's doing. We have a point here, and we made a quadratic approximation. And we want to know how far we can go, right? And without any constraints whatsoever, how far down we can go depends on what the slope is here, right? What the norm is of the gradient term, right? Because if it were a bigger norm, right, we'd have a quadratic that looked more like this, right, and we'd be able to get a bigger decrease. Okay, and the only wrinkle here is that it's not actually the norm of the gradient that matters because we are restricted in the direction we can move. And so what it is that matters, it's the projection of the gradient onto the feasible directions, right? And because it doesn't matter if I could, I could go down really fast if I went that way if I can only go this way, right? And so if the gradient is completely orthogonal to our constraint set, I can't go down at all. If the gradient is completely parallel to our constraint set, I can go down the full amount. And in between, right, I just take the gradient and project it onto the constraint set, and the norm of that determines how far I can go down. And so what I did on this slide was just showed geometrically, so our constraint set is that delta S and delta Y have to be orthogonal to each other in this case. And so the original gradient, right, was GG, right? And I showed that the projection, right, I'll write pi of GG is equal to alpha beta, right? I just split it up into these two orthogonal components. And so the length of that projection by the Pythagorean theorem is exactly equal to the length of the original G vector, right? So the length of the original gradient was √2 times the length of the G vector. It got a little bit shorter when we projected it, but it was only down to just equal to the length of this G vector, right? Yeah.
The way we constructed the p-bars, I don't remember, but were they equal to the p's at the point y?
That's right. The p-bars were equal to the p's at the current point, and right. So when I drew this picture that the p-bar was equal to within the precision of my drawing to the original p, right? So here's p and here's p-bar, and so the decrease that we get in p-bar actually has to be reflected in p. Okay. So that's the simple case. It turns out that the simple case is actually the worst case. So the norm of the projection we're going to be able to prove is always at least as large as k over √m. All right. I think so. Let me show you what could go wrong here, right? So here, when S and Y are not the all ones vector, right, the constraint set is no longer just the range of A, right? It's the range of S inverse times A, right? So let's do I have this as... Well, I'll work this out on the next slide. So the range, basically, you wind up doing a diagonal scaling of your constraint set. So the constraints wind up being A transpose capital Y delta Y is equal to 0, and delta S is equal to S inverse A delta X. Right? These basically come from the Hessian, right? And so we get that it's no longer two orthogonal spaces that we're projecting onto, which could be good or bad, right? So if we were, in here, right, if the gradient vector were in here, the sum of the projections would have a bigger norm. I've drawn a case where the gradient vector is in the obtuse angle, so the sum of the two projections can actually be substantially smaller than the length of the gradient. But the gradient got bigger, right? And so you can show that the gradient getting bigger always compensates for the lack of orthogonality. Okay? I think, so that's the part of the proof that has the largest amount of just plain calculation in it. So I'm going to skip that part of the proof for time and just ask you to believe me that the norm of this gradient vector is lower bounded by k over √m. Right? So in general, the norm of the projection of the gradient vector onto the feasible set, right, is going to be at least k over root m. And I'm going to state that without proof. And then we'll come back and finish the proof after a brief break. Oh, I'm sorry, a question? I'm sorry, back to which slide? This one? Right, so the gradient vector was the all ones vector multiplied by k over m. The 2 norm of the all ones vector is the square root of m. Multiply that by k over m, and you get k over root m. Right, so this was here. We got m plus k times the all ones vector from P1, and we got minus just 1 times this from the other P2, right? And so m plus k over m minus m over m is k over m. I'm sorry? This term and this term? Right, so this is a spherical quadratic. And so the amount of decrease is going to depend on what is the ratio of the Hessian to the gradient, right? And so we know what the Hessian is, right? It's gonna be twice the identity here. And so I'm just talking about the norm of the gradient. All right, so let's take a brief break, and we'll come back in a couple of minutes. All right, so let's get back started again. I proved for a very simple case and waved my hands for the more complicated case that the norm of the gradient, or the norm not of the gradient, but of the projection of the gradient onto the feasible step directions, is at least k over root m, right? And so what that means is that we have the step size problem is going to be something like minimize over t minus t times the norm of the gradient, k over root m, plus t squared, right? Because we know that the quadratic part has Hessian 2, or twice the identity, right? And so we can just solve that, right? So for example, if this were just 1, right? So if it were minus t plus t squared, this would be t times t minus 1, right? And its minimum would be at t equal to 1/2. And you would get a half times a half equals a quarter as the value of the minimum, right? And so if the norm were 1, then that's what we get. So because we can solve this case nice and easily, we're going to take k and assume k is equal to the square root of m. And so that means that we're always going to be able to choose the step size of at least a half, right, because this is just a lower bound, and get a decrease of at least a quarter, right? So the step size is greater than or equal to half, and the decrease is greater than or equal to a quarter on every step. Right? The other thing to point out, I've been ignoring the ellipsoid constraint for a while, but the ellipsoid constraint was just that you didn't go farther than a distance of 2/3, right? And so the step size is a half, and the half is less than 2/3, so we always have a feasible step here, right? If the gradient turned out to be, we always have a feasible step if the gradient is at its bound. If the gradient's bigger than the bound, we might run into the step length constraint, but all we have to do is scale back until we hit the step length constraint, and we'll still always get at least a decrease of a quarter. Okay. Yeah? Right. Here. The absolute value of the decrease is at least a quarter, because it's unclear from the English whether I mean minus a quarter or a quarter when I say the decrease. Yeah?
So what was the point of the ellipsis constraint if we can satisfy it without? like enforcing it?
Oh, so the point of the ellipse constraint was to make sure that we stayed within the region where our upper bound was valid on the log function.
Okay, we could have said that we had a box constraint for that.
That's right. We had a box constraint for that initially. Oh, the reason to turn it into an ellipse constraint is so that we can, if we violate it, satisfy it just by scaling back onto the ellipse, right? Because it turns out that, just to say that we can satisfy it by scaling back onto the ellipse, right? So we're only going to be guaranteed not to have to scale back if the gradient is at its minimum, at its lower bound on its norm, right? So the ellipse constraint can be active, but we can satisfy it just by scaling back and still be guaranteed that we get at least the decrease that we claimed. Okay. And so I can just say done, right? We're QED, we have an algorithm. So just to summarize, the algorithm depends on parameters k bigger than 0 and tau bigger than 1. We picked k to be root m and tau to be 2, right? We assumed we had a feasible initial point. We repeat until the complementarity is good enough. Choose a direction by minimizing our upper bound on the potential, right? And this upper bound is tangent at our current point, and it's quadratic, so we can minimize it easily. You get a step that looks like Newton's method. Subject to some linear constraints, right? That doesn't matter. We can easily minimize a quadratic subject to linear constraints. And subject to this ellipse constraint, which if you look at it, the Hessian of this ellipse is the same as the Hessian of the bound, right? And that's exactly what lets us say, well, if we can solve it without this constraint and then just project back onto it if we need to. Okay? Then we get that direction. We do a line search for the best step length that maintains feasibility, right? It's very easy to check what the value of our potential is. It's just a sum of a bunch of logs. And update with that direction and step length and repeat, right? Until we get our complementarity down to, machine precision or something. Okay? So the algorithm is nice and simple. It fits on one page. It fits in, it actually fits in about a page of MATLAB code, right? So it's not just because I'm being, vague with my mathematical notation that it fits in a page here. And it actually works quite well both in theory and in practice. And there are some parameters to set, but we know a setting for the parameters that's guaranteed to work. So really there are no parameters that you have to set unless you feel like twiddling with them. Yeah, so does that make sense? That's the algorithm. Okay, so here's an example, right? So I started with so I'm using it actually with an infeasible initializer. That supposedly it wasn't guaranteed to work there, but it turns out to work just fine. It's just the proof that doesn't work there, not the algorithm, right? And so by spending a little bit more time, I could get the proof to work in that case. I set the theoretically valid parameters, right, which turn out to be quite conservative. And this is for a matrix with 7 constraints and 7 inequality constraints and 2 real variables. And here's the path, right? If you remember what the central path looked like, we find the central path on the first iteration and go, nice and smoothly down the central path from then on. So that's kind of cool. If we look at some diagnostics, we're always taking step length 1 with these conservative parameters. So I checked to make sure it's a valid step, but in fact it always is. If I calculated the potential after each iteration, and if you look from, let's say, step 11 to 30, right, that's 20 steps. It goes down by about 10, so it's going down by about a half on each iteration instead of a quarter, which is what we proved it would do. So we're actually doing better than the proof, but the proof is actually doing a pretty good job of analyzing the behavior of this algorithm. The gap starts out at single digits, and it goes down to something like 10 to the minus 3 after 30 iterations, right? And so that means that the things that are supposed to be 0 are around 10 to the minus 3 instead of 0. And for this problem, right, if you look at it, you actually visually can't tell the difference between that and the solution. Okay? But if we go with slightly less conservative parameters, right, you can see maybe 7 or 8 distinct points here. Right, so instead of setting k to root m, I set it to be almost as large as m. I set tau to be 1.95, so a little bit less of a constraint on the step length. Same problem, solves it in 7 or 8 iterations, right? So after 7 iterations, it gets to the same solution quality that the other one did after 30. After 30 iterations, the potential is down to machine precision, right? The gap is 10 to the minus 14 almost. A double gets you maybe 10 to the minus 12 as your precision. And if you keep on going beyond here, the algorithm thinks it keeps getting better, right? It'll tell you it has a gap of 10 to the minus 150. But that's because the round-off error is it's actually managing to get the round-off error to go in its favor, right? It's finding things that when you multiply them, they round off in a way that makes you appear to get a better potential than you actually do. So that's kind of cool. And so this is, it's actually, I think, an extremely, both the proof fits in one lecture, modulo the pieces that I skipped for time. The algorithm fits on one page, one slide, or one page of MATLAB code. So it's, to me, a very beautiful algorithm and analysis. And if you compare that to the 2 chapters that it takes Boyd and Vandenberg to analyze the other algorithm, I think it's even cooler. So any questions about this algorithm or the proof? So I wanted to stop with just a quick commentary on when is interior point useful, right? So interior point algorithms, they're based on Newton's method. Newton's method, at least naively, is cubic in the smaller of the number of variables and the number of constraints. So unless we can take advantage of some structure in the problem, we're limited to maybe 1,000 or a few thousand variables, right? If we, for 1,000 by 1,000 matrix, it takes on the order of 1 billion floating point operations to invert, and it goes up cubically from there, so you can't go. Actually, the thing that makes my MATLAB crash first is the fact that you can't fit the matrix into memory anymore, right? But it turns out that structure is often present, right? So you can do, millions of variables if it turns out that you can quickly solve that Newton system. And quickly might mean, for example, that you know about a sparsity structure in your constraint matrix, or you know about a low rank structure, or maybe low rank plus sparse, and you're able to invert that system, solve that system faster than the naive cubic. The other thing to point out is that the convergence rate of these things, it's just on a totally different level than the first order methods that we were discussing before, right? So even the accelerated first order method, the best thing that you could hope for was that you would need 1 over the square root of epsilon iterations to get accuracy epsilon, whereas here we get log of 1 over epsilon, right? So here's a helpful plot of log epsilon and square root of, right? Log of 1 over epsilon and square root of 1 over epsilon. And so you can see, by the time you get up to here where you want 1 part in 10 to the 6, right, which is a perfectly reasonable accuracy requirement, you need 1,000 iterations of the gradient method, and we're hovering down here around tens of iterations with the interior point method. And this here requires a very smooth, right, the first order accelerated method. To get this rate, it requires a very smooth function. Here, this is no smoothness whatsoever, right? It's a linear program, so has, sharp boundaries where it's not differentiable. So, of course, the iterations are more expensive. They're Newton instead of a gradient calculation. But so basically what you want to do is, for your particular level of accuracy, look at whether you're going to pay more for going to the Newton or pay more for going for thousands of iterations, right? And so in particular, if you've got a moderate-sized problem that has tight accuracy requirements or quite bad conditioning, right? Because the constant in the 1 over root epsilon depends on the condition number, whereas here this is affine invariant, so it's quite insensitive to conditioning. So if you have either high accuracy requirements or bad conditioning, and you have a moderate number of variables, the interior point is going to wind up dominating. Whereas if you're in a situation where you need mediocre accuracy and you have a million variables with no special structure in your constraint matrix, you're stuck with the first order methods. The other thing is that even in large-scale cases where you can't afford to do the Newton's method, intuition from the duality can help you with algorithm design. So it's nice to know about things like Deichen ellipsoids and central paths, because it just lets you know a little bit more about the geometry of what the feasible region looks like. All right. So we have 10 minutes left. Do you want to start at all on your slides, or do you want to just call it a... All right. Happy Thanksgiving, everybody. It's the end of class. So see you after Thanksgiving. Don't forget the homework's due the first class after we get back.